Report 3 black hole. The purpose of the Lab 3 is to find the interaction between the star and the black hole and calculate the mass of the black hole. The specific thing for my lab is the star trajectory is based on my email address, and the delta t is equal to 1 day, but we have to convert it to the second unit. So it's 24 times 60 times 60 and equal to 86,400 seconds. And we also know the xy component of the star position when it moves along the trajectory. Here's the two physical principles that I used. First is a fundamental principle, Newton's second law, F naught equal to dp divided by dt. And the second is Newton's universal law of gravitation. Here specifically, we use the magnitude of the F naught times the r squared divided by the gravitational constant times the mass of the star to calculate the mass of the black hole. Here's the initial condition. We already know the gravitational constant, the star of the mass, the delta t, and the xy component of the position data. Here we are going through the calculation process. The lines here are in order to calculate the F naught. First, the delta V is equal to V final minus V initial, and the delta P is equal to the start of the mass of the star times the delta V, which is also equal to P final minus P initial. And then we apply the Newton's second law here to calculate the F naught. Here, the calculation process is designed to calculate the mass of the black hole. We know that the F naught is equal to its perpendicular and parallel component, the sum of this, and the dp dt is also equal to the dp dt parallel plus the dp dt perpendicular. When we use the product rule of the derivative here, we can calculate the F naught parallel is equal to the d magnitude p divided by dt times p hat, and the p hat is equal to the p initial divided by the magnitude of p. And here we do not need to use a product rule of derivative to calculate the perpendicular component because we have already know the F naught, and so we can calculate the F naught perpendicular is equal to the F naught minus the F naught parallel, and then we can calculate the mass of the black hole. Here's the result that I generated. The graph shows all the masses of the black hole that is generated, and I calculate the average number of the mass of the black hole is equal to 1.13 times 10 to 34 kilogram. I also calculate, my code also generates the F naught perpendicular, and F naught parallel. Here's a comparison. Now, NASA tells us that a typical stellar class of a black hole has a mass between about 3 and 10 solar masses. The mass of the star is 2 times 10 to 30 kilograms, and so the predicted mass of the black hole is within this range. But actually, you will see that my mass of the black hole is about 1,000 times larger than the typical stellar class black hole. I don't know whether it's there's arrow here or not, but I think it's also reasonable because it might not be a typical stellar class black hole. And here's the conclusion. So when I run my code, you will see that the arrows, first they are very small, almost invisible, and then they grow larger, but when it approaches the end, it becomes very small and you simply cannot see it. So here's the thing that needed to improve, is that I want to find the proper error scale that make the direction of the three forces visible throughout the entire circular motion. And my conclusion is here, we can use the data of motion of the star to calculate the mass of the black hole. And the mass of the black hole will oscillate in a narrow range, but we can calculate it according to the average mass of the black hole. Here's the answer for this question. First is what does it mean question, whether net force is different from the rate of change of momentum. I think they are different. We know that F naught is equal to the dp divided by dt, and its perpendicular and parallel component are also corresponding to dp dt parallel and dp dt perpendicular, but P is measurable. It is directly related to the motion of the stars. We can use the initial condition to calculate P, like the position data and the delta T, but F naught is different. It can only be calculated by using Newton's second law, which relates the motion of the stars to the F naught. And here's the answer for the what if question. If there is a different black hole that at the same location, which is mean that the R is unchanged, and the motion of the observed stars remains unchanged, which is mean that the orbital is unchanged, and the interaction between the black hole and the stars is unchanged, so the F naught must be unchanged. So in my opinion, the mass of the black hole is the same and it cannot be different. Thank you for watching.